Okay, so this is the Zoom meeting for Physics 231C. We're here at the end of the second week of November. This week we've been studying solids and liquids. The reading quiz is due at the end of today. And then the problem set for chapter 10, solids and liquids, is due at the end of Monday. We're sort of approaching Thanksgiving, so we will finish chapter 10 now and chapter 11 next week, and then a little bit of chapter 12 takes us to Thanksgiving. And then after Thanksgiving, there'll be the third midterm exam. And then we have a couple of weeks in December. Final exam week is the second week in December. The final exam is scheduled for December 14th. Thursday, December 14th. That's not our choice. That's dictated by the registrar's office. Now, somebody asked me to show how to estimate your current grade if you're enrolled in the course. So here's how to estimate your current grade. Now, remember, this is somewhat not accurate because it only has two midterm exams. There'll be another midterm exam plus the final exam, plus some more homework assignments. So, the course isn't over yet, so you can't determine what your grade is, but this will give you an estimate of how you're doing so far. Click on grades to find out how many points you have on the problem sets, and add up all your problem set points. Divide that by the total number. That would be for problem sets 1 through 7. You've already finished problem set 7. You're working on problem set 8 now. The total number of points possible on problem sets 1 through 7 was 287. So to estimate your homework percentage, take your total problem set points, divide by 287, multiply by 100 to convert it into percentage. Then you have the points from the two exams. So again, go to grades, add up your exam points for the two exams, divide by 24, total possible, multiply by 100 to convert it into percentage. Then your approximate score as of today would be estimated by, I really should say here, not equals, but approximately equals. Approximately equals, because this is only an estimate after all. Take 0.4 times the homework percentage plus 0.6 times the exam percentage. That'll give you a number somewhere between 0 and 100. So that's your kind of approximate score. Now remember the grading scale, which was published in the syllabus, you can look it up in the syllabus. Above 92 is a 4, above 84 is a 3.5, 76 is a 3.0, 68 is a 2.5. So take your approximate score and fit it onto this grading scale to get an idea of what your course grade would be as of now. But remember, this is only an estimate. It's only approximate. All right, so that's where we are today. And now, as usual in the Zoom meeting, we'll go over some examples for the chapter that we're studying right now, chapter 10. These are problems taken from the problem set 8. So first of all, you need the equations from chapter 10. So when you read chapter 10, you should have written down the important equations. Let's take a look at some of these equations. Chapter 10 is fairly long. It has 6 parts, 6 sections. The first section is called states of matter, solids, liquids, and gases. And there's an equation that defines mass density. Rho, we usually use the Greek letter rho for mass density. It's just the mass divided by the volume gives me the density of a sample of matter. The unit is kilograms in the numerator, meters cubed in the denominator. So the unit of density is kilograms meters to the power minus 3. Section 2 is on solids. Now, solids are sort of incompressible, but they're not completely incompressible. They are somewhat elastic. They can be stretched or compressed. And there are 2 parameters that are defined to describe elasticity of a solid. How compressible is it? There's Young's modulus. So this is relevant to a sample of matter, which is a long, thin sample. And then there's the bulk modulus. So this estimates this elasticity of a sample of matter that is not long and skinny, but just kind of a 3-dimensional volume. So for any material, there's a parameter y called Young's modulus. And the amount that the material will stretch due to a force F is given by this relationship. It's an approximate relationship, but for any material, there's a appropriate value of y, Young's modulus. And then in the case of a volume, it's compressing on all sides, compressing the volume in all directions will reduce its volume. And so the relation between the force and the change in volume involves this constant B, which again is a constant. Well, it's not a constant, it's different for every solid, for every material, but for any material, there's a constant value of B. So there's a value of B for a large box, or large cube, I should say, or for a small sphere, for any size and shape, this equation relates the change in volume and the force with a constant of proportionality, B, which is a constant for that material. Then we turn to fluids, liquids. Fluids, strictly speaking, can be liquids or gases. So the same sort of equations hold for liquids and gases. Section 3 is on pressure. Pressure is defined as force divided by area. So the unit of pressure is Newton divided by meters squared. The numerator is force, that's Newton. The denominator is area, so that's meters squared. Now that's given a special name. A Newton per meter squared is called a Pascal, named for Monsieur Pascal, French scientist of the, I guess, probably 18th century. There's an equation which shows how pressure increases with depth in a fluid. So if you have like a lake or something, you have some pressure at the surface, P0, that'll be atmospheric pressure, presumably. So that's the pressure at the surface, P0. And then as you go below the surface, the pressure increases. So if you go a distance d below the surface, that would be the depth. The pressure down here would be the pressure at the surface, that's atmospheric pressure, plus the density of the lake water times G times D. Section 4 is very important because it'll appear on the homework assignment and on the next exam, buoyancy. And the understanding of buoyancy goes way back to the Greek mathematician and engineer and scientist Archimedes. Archimedes' principle says there's an upward force of buoyancy on an object submerged in a fluid, and the strength of the force is equal to the weight of displaced fluid. So that's Archimedes' principle, and we'll be using that equation over and over again in the homework problems and in the exam problems. Section 5 is on fluid motion. So now we're talking about let's say liquids in motion. This is all about liquids that are not moving, liquids in static equilibrium. But what about when a liquid is flowing? That's the characteristic of a liquid or a fluid as opposed to a solid. It can flow, so it's fluid. It's able to flow. And there are two important equations for fluid motion, the continuity equation and Bernoulli's equation. They're both sort of conservation laws. They say that in a flow, some things are constant. So the continuity equation says the volume rate of flow is a constant. In other words, fluid doesn't disappear someplace or just appear out of nowhere. Any fluid that there is had to get there by flowing to the point you're considering. So that's a continuity equation. That's a conservation law. Any fluid flowing to a point, well, it also has to flow away from that point. Otherwise, it would be accumulating at that point. Bernoulli's equation is equivalent to the conservation of energy, although it doesn't look like it. But in fact, it's equivalent to the conservation of energy. It's an application of the conservation of energy. And it says that on a streamline, pressure plus 1/2 rho v squared plus rho g times y, the vertical component, the vertical coordinate, I should say, is constant. You can sort of see this reminds you of kinetic energy. It's actually kinetic energy divided by a volume. This reminds you of gravitational potential energy. It's the gravitational potential energy per unit volume. And what's this? Well, that's the work. So this is really related to the work kinetic energy theorem. And that's called Bernoulli's law or Bernoulli's equation. And then there's a final section about surface tension and viscosity. That's a somewhat, those are more specialized subjects. So sections 1 through 5 are the most important. Section 6 is kind of a sideline. Surface tension and viscosity. For example, one of the equations is Poiseuille's law. Monsieur Poiseuille defined a material property called viscosity, eta, And this gives me the volume flow rate through a pipe where the pressure at the two ends of the pipe are P1 and P2. The radius of the pipe is R. The length of the pipe is L. And then there's a material property, which is a constant. At least it's a constant for whatever material you're talking about. It may be different for different materials. Some materials may have higher viscosity, some materials may have lower viscosity, but for any given material, there's a value of viscosity called eta. All right, now let's look at some example problems. Oh, first of all, there are the hints for problem set 8. They're published in the hints folder in the usual way. So, you know, for a lot of the problems on problem set 8, they come from chapter 10. And so here are the hints for those problems. They may not be in exactly the same order that they appear in the homework assignment. So you may have to sort of search around to find the right hint for the right problem. But anyway, there's a little label which will give you an idea of what the problem's about. But I won't go over those in the Zoom meeting. They're just in the hints folder as usual. But now let's look at some problems from problem set 8. Here's an example involving buoyancy. Calculate the work that must be done to push a cubical block of wood down below the surface of a lake. So you have a block, let's say a cube of wood, it'll float in water. So here's the equilibrium, the block floating in the lake. And for that, the net force on the block is 0. It's just floating there. What forces are acting on the block? Well, there's gravity pulling it down. So it'll be the mass times g, the acceleration due to gravity. That's the weight. But there's the buoyancy force pushing it up. The buoyancy force is the upward force exerted by the water. So the water is pushing it up. So you have a force diagram like this. You have a downward force, that's the weight, gravity, and an equal upward force so that the net force is 0. And this has to be the buoyancy force. Whereas this is mg. Now by Archimedes' principle, the buoyancy force is equal to the weight, not the weight of the block, but the weight of the displaced water. So it's the weight of this amount of water. You know, the block is floating there in the water, so it's displacing an amount of water equal to this volume, part of its fraction of its volume. And the weight of that amount of water is the upward force on the block, according to Archimedes. All right, so that's how we start. And now you're going to push it down. So in other words, you're going to put your hand on the top of the block and push it down to a depth where the upper face of the block is distance L below the surface. So you're going to push the block down by a length L, where the block is L by L by L. So you're going to exert a force on the block let's call that force F. That's the force that you're exerting. Now, meanwhile, we still have the gravitational force, mg, or g, I guess I should say gm, pulling it down. And you still have the buoyancy force. So again, you have the buoyancy force pushing it up. And again, if it's in equilibrium, I mean, if you're holding it there, in other words, if you're holding at that point and it's not moving anymore, then the net force has to be zero. So the combination of these three forces would be zero. So let's, here are the pictures. In any physics problem, we start by drawing a picture, or in this case, two pictures. Now let's look at the equations. Well, for the equilibrium, before you start pushing the block below the surface, you have net force equals zero. And the net force is minus mg, that's the weight of the block, plus the buoyancy force, which is the mass of the displaced water times g. That's Archimedes' principle. Now I can convert this into, since I know the volume here, let me convert this mass into density times volume. So m is rho L cubed, where rho is the density of the wood. And then let's convert this mass of water is rho times L cubed, only it's not all of L cubed. It's only the volume below the surface. And this rho is not the rho of the wood, it's the rho of the water, because I want the mass of water by Archimedes' principle. So I have rho W. How much of the block is below the surface? Well, area L squared times length L minus Y0, where Y0 is the Y coordinate of the upper surface. So it's only this part of the block which is below the surface displacing water, so that would be of length L minus Y0. So length times height times width, the height is L minus Y0 times G. And that has to be zero, so you can solve for Y0. So that tells you where the block starts out before you start pushing it down. Okay, fine. Now you're going to push the block down, and that will require work, because there, as you push it below the surface, there's an upward force. The buoyancy force then becomes larger than the weight. So now there's an upward force. You have to exert that force downward to push it below the surface. So you're pushing down with a force F in the Y direction. That's the force that you exert in the downward direction. And it's moving down by an amount delta Y. So this is the amount of work that you have to do to move the block down by a distance delta Y. And now you have to add up all the distances until the block is length L below the surface. So you have to sum F sub Y delta Y, where F sub Y is the force you exert to hold the block at a coordinate Y, and delta Y is the amount you're pushing it down, the extra amount you're pushing it down, and you have to sum over all of those little sections of the complete length from Y naught to minus L. I mean, the complete displacement. Actually, it'd be the complete coordinate of the upper surface, starting at Y0 and ending up at minus L. So to get Fy, you do the same calculation as here. You have Fy as the weight, or let's say it this way, Fy minus the weight, because that's a force which is downward, plus the buoyancy force, so that's an upward force, has to all add up to zero. Well, you can solve for Fy. And then the work done is the sum Fy delta y. Now, actually, the way to do this problem is to view it as two parts. First, you push the block until it's completely submerged. So the first part of the problem is push the block from y0 to 0. You push it down until it's completely submerged. So for y, starting at y0, going down to 0, that's the work W1 necessary to get the block completely submerged. Okay, now there's W2. That's the force that has to be exerted to push the block by a length L below the surface. And you'll be doing positive work in both cases, so the total work will be W1 plus W2. So as usual, we write down the necessary equations. This is really the necessary equation. And then we start doing algebra. We start putting in the various expressions that make up this equation. Now, this involves summing all the y values here from y0 to 0, and here from 0 to minus L. And that's where the problem gets difficult, figuring out how to sum over the y values. In the case of W1, it's more complicated because the force depends on y. If the force doesn't depend on y, then the sum of all the little y displacements is just the total y displacement. But if you have the sum of y, the coordinate, times delta y, the displacement, that turns out to be minus 1/2 times the total displacement squared. So you're going to need these two tricks to do the sum over y. It's a little easier in case of W2 because in that case the force doesn't depend on y. So you just need this fact that the sum of all the small displacements is just the total displacement, which for the second part of the problem is just from 0 to minus L. So that would be a displacement of minus L. All right, so that's an example of buoyancy, calculation involving buoyancy and Archimedes' principle. And it's a little tricky because you have to divide the problem into two parts. When you're pushing the block down to the surface of the lake, plus when you're pushing the block below the surface of the lake. Here's another example. This is also buoyancy. This is the famous story of Archimedes and the king's crown. In the famous story, Archimedes proposed to weigh the king's crown underwater to determine if it was pure gold. He actually determined the material the crown was made of by a slightly different method, but this is a method he could have used. It would have been a way to determine if the crown is 100% gold or if it was somehow some kind of mixture of gold with some other less expensive material. So what it says in the problem, suppose the weight of the crown is W1 in air and W2 underwater. So he can measure the weight of the crown using some kind of balance when it's just in air. And then he would balance the crown with some known masses. Or he can measure the weight of the crown when it's placed in a glass of water or a little container of water. And then he would balance the container with the crown inside against some known masses. So here we would measure W1, here we would measure W2. So those are known. And it says, suppose the crown is pure gold. That's part A. Or part B, suppose the crown is 75% gold and 25% silver. So that's part B. So you draw a picture for part A. No, you draw two pictures for part A. And those same two pictures apply to part B, but the two pictures correspond to in air or in water. So as usual, we start by drawing pictures. So here are the pictures. And now we start writing down the equations. So how would you measure, or how would you write an equation for W2? We're going to measure W2. How would you relate that to the density of the material making up the crown? Now you're going to have to look up some densities. You're going to need the density of water. Everybody knows the density of water. The density of water is 1,000 in standard units. Standard units are for mass, kilograms, and for length, meters. So the standard unit of density is kilograms divided by meters cubed. And water has a very simple value of density. It's 1,000. In other words, 1 cubic meter of water weighs 1,000 kilograms. No, it's not a weight, it's a mass. So one cubic volume of water, one volume of water, 1 meter by 1 meter by 1 meter, 1 cubic meter, weighs has the mass of 1,000 kilograms. 1,000 kilograms, that's a metric ton. So a meter by a meter by a meter, that volume of water is too heavy for you to lift. You can't lift it. You can't lift a metric ton. All right, so the weight in air will be the density of the gold times its volume times G. And the weight in water will be the density of gold times its volume times G minus the buoyancy force, which is the rate of water times V times G. So by putting it in the water, the weight as measured by this scale would be reduced by the buoyancy force, which is the density of water times the volume times G. All right, so, you have to look up the densities of gold and silver. Let's suppose W1 has been measured. Let's say it's measured to be 31.9 newtons. Then this equation will tell you what V is. So now you know V. And then second equation, the second measurement, W2, so it has some value of W2, that will tell you the unknown, the unknown quantity, and the algebraic expression will be the density of the alloy. What you have here is really two equations with two unknowns. And one of the unknowns is the density of the alloy. So by measuring W1 and W2, you can apply algebra and figure out the density of the alloy. And then you can see, is it the same as the density of gold? Or is it less than the density of gold, indicating that the crown was some sort of alloy of maybe gold and silver? All right, so that's another problem involving buoyancy, and in particular, Archimedes' principle, and that's a famous story in the history of science. Archimedes and challenged by the king to measure his new crown and determine if it was pure gold. And Archimedes had to figure out how to do that. He actually used a slightly different method. But anyway, this was a method that he could have used. You will read all about Archimedes and buoyancy in the secondary textbook, the textbook called Unifying the Universe. Archimedes was really great physicist, mainly remembered as a mathematician, perhaps, and also an engineer. But he was also a very important figure in the history of physics. So you'll read about that in Unifying the Universe. Here's a third example from the homework assignment. This also concerns buoyancy. So all of these examples are examples of buoyancy. You have two blocks of wood, one of which floats in water, and the other one sinks in water. So let's say they both have the same mass. So you have two blocks of wood, equal mass, different volumes. The one with the larger volume has a smaller density, and therefore it floats. An object floats if its density is less than the density of water. But the second mass has a smaller volume, and it sinks. It sinks in water because it has a density greater than the density of water. We tend to think of wood as floating, but there are different kinds of wood, and some kinds of wood are more dense than others. So there are some kinds of wood which will in fact sink in water. And they're tied together by a string, and we'll say the tension in the string is T. So we're given the masses, we're given the volume of the one that's sinking. The one that's less dense than water will hold up the other one so that the combination floats. So the two blocks are floating together with some fraction of the lighter block or the less dense block, some fraction of it is underwater. That's a given quantity. And so there's the picture with labels. We always draw a picture with labels. We don't put the numbers on the picture. We just put the labels in terms of symbols. And then maybe over on the side, we write down the values of some of the labels. So M is 0.5 kilograms. This M is 0.5 kilograms. This volume is 450 cubic centimeters. The amount of this block, which is underwater, is 0.7. So here's a picture. Here are the parameter values. It's better not to put the parameter values on the picture because it just clutters up the picture. Can't really tell what's going on. And now we write down the equations. And the equations are very simple. This is in equilibrium. So the net force on A is 0. The net force on B is 0. That gives me two equations. The net force on A, well, let's do the net force on B first. It's the tension in the string pulling it up, because the string can only pull an object, it can't push an object. So T is pulling up, so that's a positive force. Gravity is pulling it down, so that's a negative force, minus mg. Buoyancy is pushing it up. That's rho times the volume, in this case, the entire volume, because the whole volume is submerged, times g. So rho times v times g, that's the mass of displaced fluid. No, That's the weight of displaced fluid. Mass times G. And the whole volume is displacing water. So it'll be the density, the mass will be the density of water. I know that. That's 1,000 times the volume. I know that. That's 450 cubic centimeters. So that gives me one equation. I'm trying to calculate T. That's the problem. That gives me one equation with one unknown. So am I finished? Yeah, I'm finished for determining T. But I also want to determine what's the volume of this upper mass. And that doesn't appear in this equation. So I need another equation. Well, the other equation is to write down that the force on the upper mass is 0. So the tension of the string is pulling it down, because a string can only pull an object, it can't push an object. So if the string is connected to the mass at this point, the tension will be pulling it down. That's a downward force, so that's a force minus T. And then there's the weight. Well, this has mass m, so the weight is mg, and that's a downward force, so that'll be force minus mg. And then there's the buoyancy force, which is the weight of the displaced fluid. So that'll be the density of water times the volume of displaced fluid, which is a fraction of this volume, which is given as 0.7. So plus a fraction of the volume of A times G. So this is the buoyancy force. The sum of these three forces is 0. So there I have one equation with two unknowns. T is not given in the problem. VA is not given in the problem. So here I have one equation with two unknowns. However, the first equation told me the value of T. So putting in the value of T here I have one equation with only one unknown, namely VA. So you can solve for both of these. And that's the problem.